Hello, everyone, and welcome to the official MultiMech 18.1 release webinar. Introducing myself, my name is Hayden Cornwell. I'm an application engineer here at MultiMechanics, and I work on making sure the customers are successful in using MultiMech. Accompanying with us today is the president, co-founder, and CTO of MultiMechanics, Dr. Flavio Souza. He'll be listening in during the main part of the webinar, and at the end, he'll be here to answer some of the questions you might have. Regarding the questions, please note that using Zoom, on the top bar, you will see there's a Q&A button. This is where you'll be able to ask your questions. There's no need to wait to the end to ask your questions. So if you have a question for the middle of my webinar and you don't want to forget it, go ahead and drop it in there. And at the end, we'll go through all the questions and answer them. And we also have a few questions that were asked beforehand, so we can also read those off and answer those as well. Okay, without further ado, let's resume the webinar. So today we're going to go over the background of MultiMech for anyone who's not familiar with the multiscale theory that we utilize. We'll outline the problems we're trying to solve and the problems that engineers have been trying to solve for quite some time. And we'll also go over how MultiMech is inserted into the analysis workflow and how we can solve these complicated problems. We'll then go into the new features of MultiMech because we find that we're constantly updating the software and it's almost difficult to keep our customers on top of the new additions we have. So we're going to go and highlight all the new features that we have with this 18.1 release. We'll then go into a demonstration of the multi-scale cohesive zone, which isn't necessarily a new addition to MultiMech. We've had that for quite some time, but it's a pretty important feature that we haven't done a full demonstration of yet. So we thought it would be useful for people to understand how exactly a multi-scale cohesive zone is implemented into your finite element analysis. We'll then go into another demonstration of the thermal multi-scale modeling. After that, we'll go into the new user interface that we've been building for quite some time. We'll go over the three tools that we currently have, which is the tube optimization tool and the RBE auto calibration tool. And then we'll wrap it all up. First, we'll go over the MultiMech overview. So the problem that we're trying to solve is that failure prediction in engineered materials is extremely difficult. And when I talk about engineered materials, I am talking about materials, say like carbon fiber, glass fiber, more complex fiber reinforced composites. But I'm also talking about materials that have been classically understood as homogeneous, for example, like metal alloys, where actually on some length scale, there actually are imperfections and discontinuities within the material that can be modeled using multi-scale simulation. And the issue here is that with these materials, damage starts down at the microscale and slowly propagates up to larger length scales. An efficient way to minimize the amount of physical testing is the use of computer simulation. However, traditional simulation tools were not made to handle complex multi-phase, multi-scale materials. And to be truly predictive, models must be able to realistically capture all relevant microstructural details, which define the material's DNA, and link that to the part product level. To do so, we require an FEA mesh that is way too large. So a feasible way of doing this is through a hierarchy of length scales. So what does MultiMech provide? In summary, we provide a true multi-scale solution that extends FEA down to the microstructural level with these key features. One, it's extremely accurate because at the microscale, we use FEM, which include multiple sources of material nonlinearity, and as well as advanced cracking algorithms that really help portray the physics down at this microstructural level. It's also extremely fast. This is due to proprietary mathematical formulations, as well as data compression algorithms running on the back end to reduce the computation costs. It's also integrated with a few leading commercial FEA tools as well, so you can insert it seamlessly into engineering workflows. And it's highly customizable through our unique API. So our patent pending technology places us in a unique spot because we can deliver the highest level of accuracy found in the cutting edge research code with the level of performance expected in commercial solutions. Here's an example of a true multi-scale simulation. The par is a simply supported beam. The left edge is displaying a symmetry, and each of these lines points to the location of the microstructural models in the beam. The particles are linear elastic, and the matrix is a linear viscoelastic material, and a cyclic load is applied to the beam. We can clearly see microcracks initiating and propagating along the load cycles. And each microstructure evolves differently depending on the loading history they experience. This is key to predictive simulation of heterogeneous history-dependent materials because failure is highly nonlinear, and the loading may induce microcracks, which in turn change the material stiffness, and as a consequence, the load will be spatially redistributed as the next solution step changes. We can clearly see that in this demonstration as the stiffness goes down after each load. As a benchmark example, consider this gear. It's a finite element model, and it was used to model impurities in cast iron. This model contains 20,000 independent microstructural finite element models, which results in a nearly 19 million degrees of freedom for the entire simulation. Each microstructure, also known as a representative volume element, RVE, can initiate and grow cracks independently at different locations and along different directions depending on the loading experience by their respective material points. Without these breakthroughs, MultiMech used to take 24 hours and 30 minutes and nearly 55 gigs of RAM memory. Now it only needs 12 minutes and 2 gigs of memory to run the simulation with the same exact level of accuracy. And that's running on a laptop with a single core. Of course, we've gotten some recognition for the technology, being able to speed up this type of high fidelity simulation in a lot of different trade shows and competitions. But more importantly, it's our customers that testimonials that we'll really care about. And Solve did an extensive vetting of different microstructure modeling tools, and they claim by far MultiMechanics provided the best results out of this very thorough investigation. Okay, now we have a little background on MultiMech. We'll jump right into what's new in the 18.1 release. Firstly, we have a few solver improvements. Like I talked about earlier in the webinar, we'll be going over a temperature multiscale demo. So that is a new capability that was added with the 18.1 release. We also have an automated time step refinement. This is still in beta, so is our first release of it, and we still have a lot of improvements to work on, but is something that you can now activate and experiment with when you're running simulations. So you don't have to go back and manually redefine your time step. We also have performance improvements. We find ourselves constantly finding more ways to make the code more efficient for running these simulations. So we're seeing up to 7 times speed increase with certain simulations due to these new improvements. We also have a major ANSYS extension workflow improvement that's much more seamless and works into the workbench workflow for ANSYS much more seamlessly, and it's very intuitive now. We also have a new GUI that is constantly being worked on and developed with time, but we have released it with 3 different applications for specific engineering analyses. Okay, so we'll go right into our first demonstration. And before we get into the multi-scale cohesive zones, give a little background on MultiMech's cohesive zone capabilities currently. So we have a wide range of modeling cracks. We have the traditional laws, which are the traction separation governed by bilinear, exponential, etc. And we also have the ability to do rate-dependent cohesive zones. You can use things like a viscoelastic material to help govern how your crack initiates and propagates. They apply both at the local and global scale. So the simulation on the left is a composite being loaded in the transverse direction. And we start to see some debonding from the fiber and matrix. And we also see some matrix cracking starting to propagate in between the fibers. We also have this ability on the global scale. You see on the right, we have a semicircle beam, and we see that this pre-inserted cohesive zone propagates accordingly using a viscoelastic material. It's worth mentioning that on the left, you see a good example of the automatic crack insertion because we don't need to define necessarily where the cohesive zone is. You can just create a material interface by selecting fiber, matrix, or a matrix-matrix interface. And when the certain traction or traction stress is reached, the crack will initiate and then propagate accordingly. And this could this allows for cracks to propagate freely through a homogeneous material like the matrix seen here. So normally people would use these laws to help govern and portray how the traction separation of, say, in this example here, we have a double cantilever beam mode 1 fracture test. You'd use these laws to help govern the crack path. But what a multi-scale cohesive zone does, it actually represents this crack using a microstructure. So what it does is it takes the damage seen at the microstructure level and it uses the differences in the constitutive tensor to portray how the crack propagates accordingly, and also has a unique traction separation law that is taken from this microstructure. So let's get into the live demo. So for this example, I showed a double cantilever beam. We will use this as our base model, as we can see right here. This is our base model, and what we'll try to do is represent the cohesive zone using a microstructure. In this case, we're using the standard traction separation cohesive zone, but we'll run the same simulation and try to capture the differences in the fracture toughness of this material. We'll open up the main GUI here. So this is the global GUI that designates the material properties and boundary conditions to this model. We see here we have 8 plies, 4 on top, 4 on the bottom, and they are represented by a unidirectional carbon fiber RVE. Give you an example of what that looks like. You see that it's just a fiber matrix, unidirectional fiber reinforced polymer. However, we're keeping everything linear elastic because we want to focus on the damage that's occurring at the cohesive zone level. So we made these this RVE linear elastic. The next step is to implement the cohesive zone materials. We have to define a microstructure as this multiscale cohesive zone and designate it to the cohesive zone that we designated in the global model. So we're going to do two different microstructures. The first is going to be a matrix with voids. This is somewhat relevant because a lot of times when you have manufacturing defects, you're going to have voids in certain parts of, say, the interlaminar region. So we want to see how this affects the interlaminar strength and how the fracture toughness changes when you have voids here. This model is governed by continuing damage as its main source of damage, but we're not limited to that. We can do a lot of different, a wide range of different failure and damage mechanisms. For example, we can do cracking within the matrix. We can do element failure. We can incorporate Weibull distributions and strength in the material. A lot of different options, but we'll go with continued damage for this case. The next microstructure we'll use to represent the cohesive zone is a toughened interlaminar region. So we have the same kind of matrix, but instead of voids, we will now have particulates that have a higher modulus that are a lot of times used to in interlaminar regions to help toughen the fracture, the crack propagation, and helps make the crack path a little more tortuous. So we'll see how this affects the overall fracture energy and factor within the simulation by using this microstructure. When you see here, we have the RVE, and we're going to use the same exact matrix properties using continued damage. However, we're going to have an interface, a particulate material that's represented by a linear isotropic elastic material. And we'll also have an interface between the matrix and the particle, and those will be governed by a simple elastic contact. So we'll start to see some cracking and debonding in between the particulate and the matrix in the simulation. So the first result we'll show is the matrix with voids. Before we show the microstructure, we can show the crack propagate within this simulation. You see how the crack propagates accordingly. And in this case, we're doing just a single cantilever beam, just pulling up one edge and keeping the bottom fixed. Now what we can do is, because all this cohesive zone elements are being represented by microstructures, we can actually output the microstructural results. So under it, I'll show a few different microstructures and seeing how the damage evolves as the crack gets closer to it and as the crack passes through this element and eventually deletes the element. You see here we have 4 different microstructures. Here I am printing out the continued damage results. And we'll go step by step, and we'll see how the first RVE experiences a lot of strain very early on. And we start to see some damage occur at the edges of the spheres of the voids. And then we finally see some failure going on within the voids. Now, this hits a certain reduction in stiffness within the material. So then after that, the RV will be deleted and the crack will be considered passed through it, and then this RV will no longer be relevant. So I'll delete that. And then as we keep progressing through, we see that this next RVE, which is located closer here, starts to undergo some strain. And then eventually the crack will pass through and after it fails. We'll do another example of this RVE. We see how the damage passes through, and then the stiffness now is reduced and the crack passes through. You see this example of how the crack passes through with the different microstructures. And this is valuable because you get to see exactly how it fails. You notice how with all these different RVs that has slightly different shears and tensile strains. So you start to see how things will start to fail. So you can start designing your adhesive or your interlaminar region accordingly based off of what you see going on in these results. The example we'll go over is the same model, except now with the toughened interface. So a very similar format, except now we have the different RVE here. One thing different here now is that you can see we're inserting the cracks within this result, so we get to see the cracks begin to develop on the different edges of the particulates. You see here we have quite some debonding in this stress concentration, which is expected here. And once we reach a certain stress, we'll start to see some damage start to evolve. And then we hit a certain stiffness and the RVE is then deleted. And we get to do the same thing with the next RVE. You see we hit a certain strength or distance, we have enough debonding, enough damage for the material to be considered failed. And we continue on for each one of the materials as the crack propagates down the line. So this is good because you get to see exactly where the failure is occurring and how it's occurring. But we would like to see some more quantitative data. So how exactly is changing different microstructures going to affect the fracture toughness? So what we can do is we can now look at the output of the reaction forces to actually gauge what this should put out in an experimental setting. So now we can look at the force versus the tip displacement here, and we can start to see how changing this RVE affects the fracture toughness. So we can plot all these results within a CSV file, And we can look at the difference between the two models. First, the interlaminar toughened one has a little higher stress at break, and we can see that in general, if you take the area under this curve, we have more area, which means higher fracture, more fracture energy. So it's a much tougher interface. So you can run different, say, volume percentages of particulates to see how exactly you can predict the increase in fracture toughness. You can also look at the difference in, for example, voids to gauge how changing your manufacturing process could negatively affect your interlaminar properties within your composite. So this is just the beginning of the analysis. It's a very simple graph to look at, but there's a lot of different ways you can run the simulation, and a lot of different things you can do to really gauge the sensitivity of the interlaminar region based off the microstructure. Okay, that wraps up the multiscale cohesive zone demonstration. And we'll move on to the next model that we'll be looking at. And this will be the thermal multiscale modeling. So the reason why this is important is because a lot of times with these composite materials, you do have properties that are dependent on the temperature. For example, in a lot of composites, you have viscoelastic materials that are rate dependent, but also dependent on the temperature of the material as well. And this is, this can be done for, say, thermal cycling or just looking at the properties at different temperatures. However, it's also an issue with the processing of these materials. When you cure them, you're going to have some residual stiffness within the laminate level as well as the microstructure level. And this second concept that I just discussed, we're going to go over and do a closer look through a model of a laminated composite. So go over to the blank page, and I'll bring up the model we're working with here. This is the simple mesh. It's a very simple mesh, very coarse. But what we're going to do is we're going to designate these different layers with different orientations of a unidirectional carbon fiber composite. And that was the same RVE that we used earlier, except now we have temperature dependent properties within this RVE. So you can see how we have two 0-degree plies and one 90-degree ply. So it's still a symmetric layup in this case. Here's the RVE. And we see here we have an orthotropic fiber, but now we have a viscoelastic material as a resin. So this obviously means that it's dependent on temperature. So when we're doing something, a simulation where it's curing or we're just cooling it down, we'll start to see the residual stresses, and it'll be a very accurate representation of what's going on at the resin level in the microstructure. It's also worth mentioning we can do aging laws. So we have a generic aging law that allows us to do things like curing. So we can implement a law that defines the degree of cure. So as you heat it up as a function of temperature and time, you can predict the degree of cure. And then as you cool it down, you can even more accurately gauge how changes in your processing can affect the residual stresses within your laminate. In this case, we will not use the curing law, and we'll just go with a more simplistic model, which is we're going to start off at a certain temperature, 180 degrees Celsius. We're going to decrease that temperature, and then we're going to look at the residual stresses, and then we're going to run a second time block that will do a simple extension of the laminate. That way we're going to gauge, see how the residual stresses affect the overall performance of the part after the cool down. So here are the results. Time block 1 will be the end of cure. So now it is officially at room temperature. When you start to see the residual stresses building up within the laminate level here. So we have a value of around 7 megapascals in tension and 4 megapascals in compression. Then we can also look at the microstructure and see what residual stresses are here. We see we have a lot of compression in the fiber after the cure, which is expected due to the coefficient of thermal expansion of both these materials. And the next step is to run a uniaxial tension test, and I'll change the time step real quickly here. And as I run this, we can look and see how the stresses change throughout the material. We're going to start to see that we're running it till failure. So we see the fiber start to degrade. This fiber is governed by a Weibull distribution. So we can see now that a lot of the fibers are failed at this point. So we can use this capability now for looking at residual stresses within a symmetric flat layup. We can also do more complex geometries, and we have more complex geometries that are not symmetric or not symmetric layups for whatever reason. You can start looking at how the geometry will deform as it's being cooled down. And I'll show that through another example that we did. And in this case, we only did 2 plies, 1 0 and 190. And we did the same exact cool down. And we can start to see the deformation of this plate. So if we have an asymmetric layup, we can predict the deformations of the laminate. So it gives you a little more confidence in if you're building a mechanical assembly, give you more reliability on the tolerancing of the certain parts fitting together and making sure you don't have too many deformations. And this can be done with, you say you have a resin system and a fiber. If you have all of the viscoelastic properties, aging laws of the resin, you can be predictive in seeing the deformations of the plate before actually running, doing a full cure of the geometry and building the mold, etc. So that wraps up the thermal multiscale model demo. We'll move on to the new GUI. So like we said, we have a new user interface, and this is a new interface that'll be more of a progressive rollout. We'll start releasing different applications because we want to get people slowly used to this new GUI. But basically what it is, it gives people it gives us the chance to keep it more all-inclusive. As in, right now we do use Gmesh to handle some of the meshing, even though it's automatically made. This way we can keep all of the meshing, the model, defining physical surfaces within the GUI itself, so we don't have to rely on a third party. But for the first part we're doing is we're making a few applications, the first of which is a tube application. So when you open up the new GUI, you'll see that you have the option to select tubes. This is very specific to tube geometries. So when you come to the top right, tubes, you first need to define your microstructural model. So you see here we have a fiber volume of 0.6 of like 60% fiber. Pick your fiber diameter, and you can create and define multiple resins and fibers, and you can mix and match these different fibers and resins to gauge the effect on the performance of the tube. After that, you can find the burst pressure of a certain tube, and what you do is you just put in a max pressure, a radius of the tube, liner thickness, composite thickness, number of flies, and layup angles, and you select calculate, and you'll be able to see the burst pressure of the tube. Now this does take a couple minutes, so I'll replace this with a video that will show the analysis of a tube. And you see you can have the post-processing window here. You can look at things like the different stresses, the constitutive tensor. So when things are close to failure, you get to see how they fail, stress concentrations of the different plies, see how it's distributed, etc. The next step is the tube optimization tool. Let's say that you have some design criteria of the tube, and say you're limited by outer wall diameter, you're limited by the amount of the weight you have, the number of plies, the thickness of the liner, etc. What you can do is you can put in these different variables and define a max number of iterations. And what MultiMech will do, it will randomly select a few different layup orientations, run those to try to gauge the optimal burst pressure, and using a genetic algorithm, we'll take each batch of runs and converge upon an optimal layup for the tube. So to show you as it runs, what will happen is we'll take each layup, it'll run it in the background, and then after the burst pressure is found, it'll present the results. And in the results tab, you can see what current layup is working on and the best layup to date. And in this case, we're optimizing for weight as an aerospace application. However, you can optimize for any user-defined materials, and we can customize this application for our customer. The next unique component of this tube application is the defects tool. So what I mean by defects is when you have your tube, you can define a certain percentage of elements that have defective materials. So the first step is to select your simulation or layup. So let's say our favorite layup, the results is optimization test 58 that we just ran. What we do is we pick a minimum percentage and a maximum percentage of defects. As in this case, we have 2% minimum of the elements will have defective materials, and we'll also have some runs that have 20% of the elements having defective elements. Number of subdivisions means you'll have 2 other subdivisions besides 2 and 20 in between this percentage. And finally, you select the type and number of samples of defects. As you saw in the dropdown, we have the ability to pick a resin pocket and a void. We can also do a custom defect. For example, you can do an RVE that has a weakened fiber. You can do a smaller volume fraction of the fiber. You can do a weakened interface. You can do pre-cracking, element failure early on. There's anything you can do to customize how you want to characterize the defects within your tube. And number of samples means that for each percentage of defect, so we'll have one bucket that has 2% of the elements are defective. We will have 3 samples there. What that means is these defects are chosen randomly. So we'll do 3 different models that have 2% of the elements defects picked randomly. So that way you have 3 different models with the defects grouped differently. So for example, if you have your defects more closely grouped in one model, we might have a lower burst pressure. So that way we gauge a range of values for each percentage of defects. So these will run in the background, and after all the simulations are run, we can look and then plot the percentage of defects. So we see we have 2%, 8%, 14%, and 20% defects, and we can see how there is, for each percentage, there is a certain range of burst pressure for each one. And as we expect, the more defects we have, the lower the burst pressure. And when you start gauging the range here, this is significant because a lot of times with finite element analysis, you build a model and you run it over and over again, you're gonna get the same result every time, with either the same boundary conditions, the same assumptions used. In this case, we're now bringing stochastics into the equation. We're trying to get a range of burst pressures for these different tubes. And now it's much more like a virtual test, because a lot of times you're going to run the burst pressure, you're going to have highly variable burst pressures. And that's because you have things like defects that are incorporated that have different groupings, process variation, et cetera. So you now capture these using this defect analysis tool. So that is the tube functionality. And we also have a pressure vessel capability. For the sake of time, I won't go over that because it is the same workflow as tubes. However, we used to use a pressure vessel geometry. So it's an axisymmetric geometry that you can specify the width, thickness, and length of a pressure vessel, and it'll do the same analysis where it optimizes for the layup orientation of different plies of the pressure vessel. So we have the tubes functionality, but we also have this other function called the virtual allowables tool. We found that when we have a specific family of material, it does take some time to understand the characteristics of a material and to figure out how to pick out the material properties for each constituent material. For example, in a unidirectional fiber composite, you have the fiber, which is an orthotropic material, and also the resin that experiences highly nonlinear behavior at high strains. So it's kind of tough to really characterize that because sometimes you won't have the neat resin data, the stress strain curve. Sometimes you won't have the interfacial data between the fiber and matrix, or should I say almost never have that. So in order to characterize this, you have to use coupon level data. And it's difficult because a lot of times you have to run these different these different load cases on this RVE, and you're not sure exactly what which component of the constituent material you are calibrating for. Of course, we developed workflows for this, but it is some learning curve to understand this and be able to implement it on your own. So we decided we would automate this in the background and do an automatic RVE calibration. Right now, it's only for the unidirectional fiber reinforced material, but we're going to extend this to other materials as we build upon this new interface tool. So first step is to just define the volume fraction and then the cured ply thickness. So this is just the thickness of a ply of this material. You select create and automatically create the RV for you. We also want to do this because we didn't want to make limitations in GMesh knowledge hindering people's ability to run these analyses. So we decided to handle all the meshing and geometries as well, according to the best practices that we've found with this material. So you see here we have a fiber, matrix, and an interface region. The next step is to calibrate for the properties. What we want to do is take the most, be able to take the most simplistic data you can have. So for example, on a data sheet, you'll have 0-degree tension composite data, you'll have 90-degree tension composite data, and also in-plane shear, just for a unidirectional carbon fiber prepeg. And you take the values that are very commonly found on data sheets, plug them in here, so just simple modulus and strength, and then run. And then in the background, it'll run all these, a large list of optimizations to find the optimal parameters for all the different constituent material properties. And this is something that was created internally because we do have best practices for different materials. So this is something we just translated as an internal tool and now run it automatically using this auto calibration tool. So you select run, and in this case, it takes around 2.5 hours to calibrate for the materials. But after that, you then have an RVE that is defined by the name here. In the virtual reliables, you then have the ability to take this RVE. So you can take this and you can run right now a select few layups. These are just commonly seen layups that are available, for example, from NIAR. But we're going to keep expanding this to compression tests, short beam, shear, open hole, filled hole tests, and to keep adding onto the list of standardized layup tests. So you select run, and these simulations, depending on the material and when it fails, can take anywhere from 2 to 5 hours each. So you can run all three overnight, and then in the morning you can have the results displayed here. What this will do, it'll give you the stress strain of this coupon test, it'll give you the strength, and then the modulus. And this, we wanted to keep this as simple as possible for people who don't necessarily have much CAE experience. If you're in the materials and processing, and you want to just gauge the, you want to gauge and validate and virtually test a material, you can very quickly take in the data from a data sheet, plug it in, and then very quickly find stress strain curves, modulus, strength, etc., and compare that to experimental results very quickly without necessarily doing a lot of the rigorous meshing and modeling. Okay, that concludes the new user interface, and I think that concludes the webinar. Just to give an overview of what we talked about today, we gave a highlight of the MultiMech multiscale technology, and a little background on the FE squared methodology. We also went over the new features in the 18.1 release. We went through multiscale cohesive zone demonstration, as well as a thermal multiscale modeling demonstration. And we went through the new user interface that is now available at the 18.1 release that you can use and test yourselves. Okay, I'm gonna pause sharing right now, and we will get into the question section. So we have right now one question that's in, and that question is, how do you handle fatigue? Fatigue is a commonly asked question that we get. We know fatigue is a big issue of the cause industry, and the real answer right now of how we handle fatigue is we don't have a very rigorous workflow for how we handle fatigue. It's very tough to take the materials and run, say, 1 million simulations of a multiscale model, and also being able to check these results is a little tough. And this is something that is current R&D within MultiMech. However, we can extrapolate different trends with progressive failure. For example, we saw in the beginning of the presentation how we have the beam that is being loaded continuously. We start to see how damage progresses. And using materials like multiscale, using viscoelastic materials, we can see how damage progresses and how crack grows, and give an idea of if fatigue will be problematic within a structure. So long answer for short is we don't have a current workflow, but that's something we're working on, ways we can extrapolate this. Feel free to expand on this at all, Flavio.
I think you covered the question. We are working on developing. We have some internal results already, but we still want to work a little bit more before we release it.
Okay, yeah, I understand. So we also have some questions within the chat. So Flavio, do you want to? I'm reading through this right now. Do you want to read that question aloud and talk about what your answer was in the chat?
Absolutely. We've got quite a few interesting questions. The first one was, would you be able to show similar crack propagation within the actual microstructure? And the answer is yes. I believe what was shown was that we were modeling microstructure cracking using our automatic crack insertion. But beyond that, we also have continued damage and element deletion capabilities that you can use instead.
Mm-hmm. Yeah, so I think the one you're talking about, I'm now showing on my screen, is yes, this RB right here. So we can see how the cracks are automatically inserted and propagated throughout a microstructure.
Correct. The next question would be could we use a real microstructure image from SEM or micro-CT? And the answer is yes. We don't handle that directly, but there are some software available in the market that you can generate finite element meshes out of those SEM and micro-CT. And once you have the mesh, you can import it directly into MultiMech.
Yeah, and that is also something we've done in the past for customers. So there are plenty of established workflows for different types of images too, and different microstructures and length scales.
The next question was, what is the knowledge prerequisites required for effective use of the software? And the answer is pretty simple. You only need a basic finite element knowledge to use any CAE tool. It's very similar. If you already use Abacus, ANSYS, NX, Nastran, or any other FEA software, you have 90% of the knowledge required to use our tools. The remaining 10% you can easily get in our training session, which typically takes 1 or 2 days, and you'll be up and running.
Yeah, I would say that MultiMech, as far as finite element uh, tools go, I would say it's more on the easy to learn side. There's not as many. There's not a whole lot of knobs, and it's not a huge uh, canvas to work with. We keep it very streamlined and focused on the physics going on at the microstructure. So, and hence why we're making more of these applications to streamline the process of modeling to help the users get results as quickly as possible.
Hey, now I'll have you answer the next question, which is there was a question about the displacement units.
Okay. Oh yeah. So what are the displacement units? So MultiMech does not have necessarily a preset units. So on the global scale, you can define your units based off of metric or imperial system. And depending on the units they use for pressure, you can extrapolate what the length scale is at the global level. However, when we talk about the microstructure, there is no real translation between the length scale at the microstructure to the global structure, because this is a representative volume element. You can make a microstructure that is in anywhere from the hundreds of nanometers to even millimeters, and as long as this microstructure represents the volume as a whole, you can use this. It doesn't necessarily matter how far you transfer between different length scales. So when we have displacements at the microstructure, we look at things more based on strain, which is a unitless uh, number. And when we're looking at the global structure, it's up to the user to define the units.
Very good. The next question is, can we model thin coatings? For example, the microstructure of the coating and the substrate, along with the interface between the two materials. And I think you can answer that question as well and show the picture of the coating that we have, Hayden.
Yeah. So the with the unidirectional carbon fiber microstructure.
Yes.
Yeah. So the measure is, yeah, we can model thin surfaces. Exactly how thin is up to the user. So we can see here we have an interphase region, and this is just a modeling technique we use for continuous fiber composites. We have a thin layer here, and we represent this by different properties. For example, different damage parameters, failure, etc. on this area. You can make this thinner. But of course, when we start getting into a region where the aspect ratio of this element is too large, that is when we can transfer to something like a more classic cohesive zone where you can have cracks inserted. Or like we showed today, we can do multiscale cohesive zones. So you can represent this as a cohesive zone, but using a microstructure to govern the failure and the traction separation here.
We have a couple of more questions here on our Q&A.
Okay.
Next one is, does MultiMech support standard formats like STEP, IGES, Mesh, and STL? Right now, we can import only Abacus and Gmesh meshes, but our new user interface, as Hayden demonstrated, will be able to import those CAD formats. So in the next few releases, we're going to have that capability. The next question is, what are the inputs for crack initiation and growth? Can you answer that question, Hayden?
Yeah, so the inputs for crack initiation and growth are, so it depends what type of cohesive zone that we're working with or what type of crack parameter. So like I said, we do have the traction separation laws that are classically seen. So if we're using a bilinear law, you would have to put in the same parameters that are used for a traditional bilinear law. So you have like a certain traction stress that initiates the crack, and then also separation law that governs how it progresses. We also use exponential functions So there's a wide range of different functions you can use for this, as well as using a viscoelastic material. So it's kind of hard to answer what inputs, because there's a lot of inputs you can use depending on what type of cohesive zone you want to use. And it's a whole other story when you use a multi-scale cohesive zone. But the inputs are completely up to what type of cohesive zone you want. And it's kind of a nice problem to have, that we have so many different capabilities, but there's just a lot of different answers for that question.
Very good. The next question is, does MultiMech support ceramic and metal matrix composites? The answer is we support any kind of material, basically. Because we are based on finite element model, there is no assumption on the individual constituent material behavior. So we have quite a few constitutive models implemented, including orthotropic, elastic, linear viscoelastic, nonlinear viscoelastic, elastoplastic models, and the list keeps growing every year. And so for those types of materials mentioned, we already have the models necessary to account for them.
Mm-hmm. I like the next question here. Is the microcellular foaming of fiber reinforced plastic composites. Do you want to go ahead and answer that one?
No, please take it.
Okay. As far as how to generate microcellular foaming of fiber, it's a very advanced material. So I personally don't have too much experience with that, but we have a very customizable ability to work with different microstructures. So let's say we have the microstructure I have here. This is a fiber reinforced plastic composite. If we want to look at different, more novel matrices, like we said, we can't support things like ceramics or metal materials here, but we do have the ability to represent this as another microstructure. So if we want to represent it as a more porous, either closed cell, open cell foam, for example, we can represent this here. So we don't necessarily need to have the exact geometry here. We can represent this by another microstructure. And we've made some open cell foam RVEs that we're currently implementing, and it's really customizable up to the user. We do have the automatic geometry, or the automatic microstructure generation tool, but we're not limited to what it can be created through that. Even though that has a lot of different microstructures that can be made, we can also create microstructures by hand and implement them into your models.
Yep, that was a very good answer. The next question is, do we support Ubuntu platform? Yes, we do support. We support a couple of different Linux distributions, including Red Hat and SUSE Linux, and Ubuntu as well. Typically, when it's a Linux installation, the first question we ask is, what is the version? Because many times it changes the compatibility. So in order to check that, we ask the version. Then if we don't have it, it's typically very quick to build a new installer for any new distributions.
Mm-hmm. And I think there's a follow-up that says MultiMech customer list. Not sure exactly.
We can follow up on that question later.
Mm-hmm. That's true. Okay, I think I have just a couple more questions we'll get to here. And one that we had sent in beforehand was, what kind of applications would you use multi-scale cohesive zones? I think I can take this one. So like we showed in the webinar, we applied multi-scale cohesive zones to a laminated composite, showing either defects or interlaminar tougheners within the interlaminar region. But of course, this isn't the only application. We can do things, for example, for adhesives. So if we want to study how debonding occurs through certain different adhesives, you can look at seeing how the thickness of the adhesive, are we getting adhesive or cohesive failure? And we can do this by experimenting with these multiscale cohesive zones and seeing how cracks propagate. And you can even go as far to put a cohesive zone around a multiscale cohesive zone, so you can see if the crack will propagate through the microstructure or adhesive failure, or it'll debond with the adhesive on the side, which is more on the interface. So you can do things like that to really see how you can improve your adhesive and how you can force a more tortuous crack path and get more fracture energy, or whatever you're trying to design your material for. And you can also go as far as saying, I want to model the fiber resin interface, which may not seem intuitive using a microstructure cohesive zone within a microstructure, but it's something that's completely capable within MultiMech, and we have seen people use this in order to even do a three-way multi-scale simulation in which we have a microstructure within a microstructure. Multi-scale inception, if you will. And I guess the last question we'll go over really quickly is what type of optimization is performed for the tube. We talked about the optimizer looking for the optimal solution. So do you want to answer that quickly, Flavio?
Sure. Our optimizer has a couple of different algorithms, including design of experiments and a few other nonlinear ones. The one used for the tubes is generic algorithm, which basically creates a population of different designs for the layup. And then we iterate and then create different populations based on the ones that perform it better, and then try to search for the best and optimal solution.
Mm-hmm. Yeah, that's yeah, I may have not necessarily gone over it in very much detail because I was trying to get through all the different capabilities, but thanks for clarifying that.
Absolutely.
Okay, I think we are out of time officially. I would like to formally thank everyone for who tuned in to this webinar. That being said, if you're interested if you're still interested in MultiMech, you can visit our website. We have a contact email and a contact portal that you can reach out and ask more questions regarding MultiMech. You can also have discussions about doing a trial with the MultiMech software and things like that. I really appreciate all of your time, and I look forward to hearing from you. Thank you.
Thanks, everyone.